Assalamu alaikum, dear students. In previous two lectures, we learned about sequences and infinite series. So, whenever we talk about infinite series, there is a question that whether series is convergent or divergent. Now, from this lecture onwards, we are trying to find the answer of this question. If we have an infinite series in front of us, and with the question whether the series is convergent or divergent, we are going to introduce few tests of convergence of the series. So we are going to start with the first test in this section, which is section number 10.3 of the book, and in this section integral test is discussed. So let's start with the topic formally. So in this lecture, the layout is given as follows. We'll discuss non-decreasing partial sums. Then there is an integral test. There is a theorem about this and the strategy to follow the test. And then there is error estimation, because this test does not allow us to find the exact sum of the series. It just tells us whether series is convergent or divergent. So we'll try to approximate the error. And finally, this error estimation technique leads us to find the bounds for the remainder in integral test. So first of all, non-decreasing partial sums. We are already familiar with the term non-decreasing series and non-increasing series. So we are going to discuss the series of partial sums which is non-decreasing. Okay, suppose we have this infinite series, sigma n varies from 1 to infinity, with this property, that is all the terms are non-negative, greater or equal to 0. There is no negative term in the series for all n. Then each partial sum is greater or equal to its predecessor, and it makes sense because Sn plus 1 is equal to Sn plus An, and since An is positive, so Sn plus 1 is actually greater than Sn or equal to Sn. If An is 0, then there will be the sign of inequality. So in general, we have this non-decreasing sequence of partial sums, right? So by the monotonic sequence theorem, we have the result: a series of non-negative terms converges if and only if its partial sums are bounded from the above, right? So the series of non-negative terms, infinite series of non-negative terms, converges if and only if its partial sums are bounded from the above. And this is the result we discussed in the section 10.2. So let's see. In the application of this result, we have an example. So there is an example: sigma 1 over n, and n varies from 1 to infinity. This is an infinite series, and this is another representation of this series, term-wise representation. So nth term of this series is going to be 1 over n. So for all n, this is greater than 0, because n varies from 1 to infinity. Since n is positive, so 1 over n is also positive. So as n increases, 1 over n goes to 0. So the series diverges because there is no upper bound of its partial sums. Now to see why, group the terms of the series. Now we just analyze using the corollary. We concluded that this series is divergent because there is no upper bound for its partial sums. So to see why, we are going to group the terms of the series in the following manner. So first terms 1 and 1 plus 2, and they both add up to 1.5. Okay. Now third and fourth term 1 over 3 plus 1 over 4. Okay. And this is greater than 1 over 4 plus 1 over 4. Right. and this is equal to 1 over 2. Similarly, we have this series, right? This series is 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8, and this is also greater than 1 over 8. Just replace every term by 1 over 8. 1 over 8 is less than 1 over 5. Similarly, 1 over 6 is greater than 1 over 8. Similarly, 1 over 7 is also greater than 1 over 8, and plus 1 over 8 as it is. So, now sum of these 4 terms, that is 4 times 1 over 8, is in fact 1 over 2. So this sum is also greater than 1 over 2. Similarly, we can prove that this sum is also greater than 1 over 2. So we are going to add 1 over 2 infinite times. Alright. So we are not going to have a finite sum for this series. So adding 1 over 2 infinite times, we actually have a conclusion that this series approaches to infinity. Sum of the terms approaches to infinity. Or formally, you can say that the sum of the next 4 terms and which is greater than. So in general, the sum of 2 to the power n terms ending with 1 over 2n plus 1 is greater than 2 to the power n over 2 to the power n plus 1, that is 1 over 2. So if n is equal to 2 to the power k partial sum, Sn is greater than k over 2. So the sequence of partial sums is not bounded above, right? So the harmonic series diverges. So we don't have the upper bound of the sequence of partial sums. So that is why this series is divergent. Okay. Now the integral test. We now introduce the integral test with a series that is related to harmonic series but whose nth term is 1 over n square instead of 1 over n. Now, in this case, what we are going to do, we have this series sigma 1 over n square, and term wise we can represent this series by this sum. Now, let's draw the picture of this series. As we learned in section 10.1 that we can represent every term of the sequence by a rectangle, right? So for n is equal to 1, we have this rectangle 1 over 1. For n is equal to 2, we have this rectangle, right? And similarly, for n is equal to 3, we have this rectangle. This is the lower sum. But if we compare this sum with the integral 1 to infinity 1 over x square, that is, we are going to associate a function with the nth term, that is an is equal to f of n, which is equal to 1 over n square. Okay, so f of x is 1 over x square. So since this function is continuous for every value of n, right, because n varies from 1 to infinity, so we can associate it with this integral, and this integral is actually area under the curve from x is equal to 1 to x is equal to infinity. That is the area I am shading in the red color, right? This rectangle is not included in this area, right? This is not included. So the area under the curve towards right of this rectangle is the area covered by the function 1 over x square, okay, from 1 to infinity. So this integral will give us the value of this area under the curve from 1 to infinity, x equal to 1 to infinity. So let's try to find out the value of this integral and then compare it with this series. So to carry out the comparison, we think of the terms that series of values fx is equal to 1 over x square and interpret these values as areas of rectangle, as I told you before. So Sn is equal to, now just add all these areas. We have Sn is equal to 1 over 1 square plus 1 over 2 square and so on up till 1 over n square, which is equal to f of 1 as we associated the function with the nth term. So f of 1 plus f of 2 plus f of 3 and so on plus f of n. And this is equal to f of 1 f of 1 is 1 over 1 square. So the area actually includes towards the right of this rectangle under the curve. So this is going to be 1 to n 1 over x square dx, right? Now letting n approaches to infinity, we have f of 1, value of f of 1 is 1, and as n approaches to infinity, this integral becomes integral of 1 to infinite 1 over x square. Okay, and now this is very much clear from this figure that the integral 1 over n 1 over x is less than integral 1 over infinity as 1 over x square. As we let the number of integral to infinite, then this integral, the value of this integral is going to be less than the value of this integral, because this is the lower sum, so we can see the error actually. So what is the value of this integral? Let's evaluate it. We can evaluate this integral by, I'm just going to evaluate this, b approaches to infinity 1 to b 1 over x square dx, and this is equal to limit as b approaches to infinity 1 over x square, integral of this is x to the power minus 2 plus 1, that is minus 1 divided by minus 1, and 1 to b, right? So what is the value of this integral? So limit as it is. Just apply the limits using fundamental theorem of calculus. We have, when x is equal to b, we have 1 over x minus 1 over x. This sign is negative. Negative, negative, positive. So plus 1 over 1. Because x inverse is 1 over x. So this is 1 over b. I'm sorry. This is 1 over b. Okay. Now as b approaches to infinity, 1 over b approaches to 0. So answer is 1. So that is why you can see this integral is equal to 1. Okay. So this f of 1 is 1. This integral is equal to 1. So we have the sum which is equal to 2. So that is, we have an upper bound. Okay. We have an upper bound for the partial sum of this series. That is, the partial sum is bounded from above, and from the result, the corollary of monotone theorem, we can conclude that series is convergent. Okay, so sigma 1 over n is divergent, and sigma 1 over n square is convergent. Okay, now this idea of solving this problem leads us to the integral test, and let's formally describe the test. So here we go. So this integral test is summarized in theorem number 9 of the book. So let a n be the sequence. So we must have a sequence, of course, whenever we have a series. A n be the sequence of positive terms, right? This is very important. Suppose that a n is equal to f n, that is, we are going to associate a function with every term in the series, in the sequence, where f is continuous. Now these are very important, and you must not forget it while applying this test. First of all, a n is a sequence of positive terms. Secondly, we have a function associated to each term of the sequence, and this function must be continuous, positive, and decreasing. Okay, if one of the conditions fails, then we cannot apply integral test. So f is continuous, positive, and decreasing function for all x greater or equal to n, where n is a positive integer. Then this series and the integral both converge or diverge. If this integral converges, that is, this integral has a definite value, then this series is convergent. If this improper integral approaches to infinity, that is, this is divergent, then this series is also divergent. Okay, so we can prove this result. So we establish the test for the case n is equal to 1. The proof for general n is similar. So we start with the assumption that f is decreasing. Okay, this f, which is fn is equal to an, defined by this relation. So f is decreasing function with fn is equal to an for every n. This leads us to observe that the rectangles in the figure, these are the rectangles in the figure which have areas a1, a2 up to an, collectively enclose more area than the curve y is equal to fx from x equal to 1 to x equal to n plus 1, right? Or we can write integral from 1 to n plus 1. So fx, this is the graph of fx, right? This is the graph of fx. So what is the area under the curve from 1 to x equal to 1 to n plus 1? It can be evaluated by this integral from 1 to n plus 1 fx dx. But this is less or equal to the sum of the areas of all these rectangles from 1 to n. Okay, so this is less or equal to a1. a1 is the area of this rectangle, a2 is the area of this rectangle, similarly an is the area of this rectangle in the interval n plus 1. So this is less or equal to a1 plus a2 plus an, 3 plus an, right? So we have this equation. Okay, in figure b, now figure b is drawn like this. Okay, so in figure b, the rectangles have been faced to the left, right? So we have n is equal to 1 and the rectangle is faced to the left of the x is equal to 1 or n is equal to 1. Similarly, we have n is equal to 2 and rectangle made is faced towards left. Now, in the previous case, rectangle were faced towards right. Okay, so this is n is equal to 1 and rectangle made was faced towards right. Now, and that is why we had the area obtained by adding all the areas of rectangle is greater than actual area under the curve. Now, in this case, rectangles are facing towards left, uh, right? So this is the point n is equal to 1 and rectangle is facing towards left. So in this case, area covered by all these rectangles is less than the actual area under the curve. So we can say that, and actual area under the curve is starting from n is equal to 1. So that is why we are excluding a1 because a1 is not included in this area. So we are going to start from a2. So area bounded by all these rectangles a2 plus a3 plus an is less or equal to integral from 1 to n fx, right? So this is the relation you can observe from this figure. Now adding both sides, adding a1 to both sides, we have this relation a1 plus a2 up to an is less or equal to a1 plus integral from 1 to n fx. So nothing special is done in this case. We just added a1 to both the sides to the inequality. Now, what we had in the previous slide, we had this result. That is integral from 1 to n plus 1 is less or equal to a1 to an, sum of a1 to an. So, combining these two, combining this inequality with this inequality, we have this result. Okay, so this sum a1 a2 up till an is less or equal to a1 plus integral from 1 to n fx dx. This comes from this inequality, and this is greater or equal to integral from 1 to n plus 1 fx dx, and this comes from previous inequalities. So what does this mean? So this inequality, these inequalities hold for each n, okay, and continue to hold as n approaches to infinity, right? So if now letting n approaches to infinity, so if integral from 1 to infinity is finite, the right hand inequality shows sigma an is finite. Hence, the series and the integral are either both finite or both infinite. So, if this integral from 1 to infinity fx dx is finite, then the right side is finite, left side is also finite. So this sum will be finite. As n approaches to infinity, actually we are going to have this relation. Sigma an is less or equal to 1 plus 1 to infinity fx dx. Okay, and this is greater or equal to 1 to infinity, as n approaches to infinity, n plus 1 also approaches to infinity. So fx dx. Now if both are finite, then sigma an will be finite, because sigma an is less than some finite value and greater than some finite value, sigma an is finite. But if both of them are infinite, so sigma an will also be infinite. So this gives us the conclusion that the series and the integral are either both finite or both infinite. That is, series and integral both diverge or converge. Okay. Now keep it in mind that this does not give us the exact value of the sum. That is, we don't have we cannot find the value of sigma n from this test, but this test actually allows us to conclude that whether the series is convergent or divergent, right? So this is the integral test. Okay. Uh, Now, in order to implement, we have an example. Show that the P series, which is given by this series, sigma n is equal to 1 over 1 to infinity, 1 over np, is equal to, term wise we can write this series as the sum 1 over 1p, 1 over 2p plus so on. P is a real constant, converges. Okay, this series converges if p is greater than 1 and diverges if p is less or equal to 1. So we have to discuss three cases: p greater than 1, p equal to 1, p less than 1, right? And it converges only when p is greater than 1. We have to prove this, and diverges when p is equal to 1 and p is less than 1. So let's start with p is greater than 1. So if p is greater than 1, then fx is equal to 1 over xp is a positive decreasing function. Okay. If p is greater than 1, then this is a positive decreasing function. For example, if we have p equal to 2, for example, then this series will become 1 over n square, where n raised to 1 to infinity, right? And what is the series in this case? 1 over 1 square, 1 over 2 square, 1 over 3 square. So you can see this is decreasing series. Similarly, if we have p3, we will have n cube here, and again every an plus 1 is less than an. So again the series is decreasing. So if p is greater than 1, we have the series 1 over xp is a decreasing series, and its all the terms are positive. So two of the conditions are satisfied of integral test, that is, the series is positive and decreasing. And the next property, that this function is continuous as well, right? From 1 to infinity, this is continuous as well. So it can be written in this form, and by taking the limit, as I mentioned in the previous slide, you can take the integral antiderivative, and then by applying the limits, we have the answer of this integral is 1 to p minus 1. Okay. So what does this mean? Since this integral has a finite definite answer, that is, this integral is convergent, so this means the series is convergent. Okay. Now again, this is very important. We emphasize that the sum of p series is not p minus 1. This is very important to note. This is the value of this integral. This is not the value of the sum of the series. Okay. So this is very important to note, that the sum of p series is not 1 over p minus 1. So the series converges. This only concludes that series converges. We don't know the value it converges to. That is, we don't know the sum of the series, value of the sum of the series. Okay. So keep it in mind. This test just tells us that whether series is convergent or divergent. And if series is convergent, it does not tell us the value of the sum. Okay. Well, next case. P less or equal to 0. So if P is less or equal to 0, then series by the nth term test divergent. Okay. When this is less or equal to 0, that is when P is negative. Less or equal to 0, or when 1 with NP will become sigma 1, where n varies from 1 to infinity when P is equal to 0. This is the case when P is equal to 0. This series is divergent. Okay. And what if when this is negative? And P is negative, let P is equal to minus k, where k is positive. Okay. Where k is greater than 0. N to the power minus k. Right. Now, P is negative. So, we are going to have this series as, for n is equal to 1, we have 1 to the power k, plus when n is equal to 2, we have 2 to the power k. K is positive. 1 over 2 to the power minus k means 2 to the power k. Okay, plus 3 to the power k. Okay, plus so on. And k is positive. Right? So just keep it in mind, k is positive. So this is also divergent because it is increasing indefinitely, right? So this is also divergent. So this is divergent by nth term test, because nth term approaches to infinity as n approaches to infinity, right? So nth term in this case is n to the power k, where k is positive. So nk approaches to infinity as n approaches to infinity. Similarly, nth term in this case is 1. So sum of 1 infinite times will give us infinity. So in both the cases, P less or equal to 0, the series is divergent. Now, what is left? We are done with P greater than 1, where series is convergent. So we are done with P greater than 1. We are done with P less or equal to 0. So if we draw this, this is 0, this is 1. So P greater than 1 is this portion, and P less or equal to 0 is this portion. So what if P lies in this interval, that is between 0 and 1? Okay, so what's going to happen? Now in this case this is convergent, in this case this is divergent. So let's discuss this interval. P is equal to 0 has already been discussed, okay, in this. And now P is equal to 1, and when P lies between 0 and 1, that is open interval 0 and 1. Okay, so first discuss P lies between 0 and 1, and this implies 1 minus P is greater than 0. Okay, and this implies integral from 1 to infinity 1 over x p dx is equal to, just evaluate this. We have 1 over 1 minus p limit of this. As b approaches to infinity, this leads us to infinity. So, since p minus 1 is greater than 0, so let me tell you p minus 1 is less than 0, I know. So, let me evaluate this for you. Okay, so 1 to infinity, 1 over xp dx is equal to limit b approaches to infinity 1 to b 1 over x to the power p dx, right? And this is equal to, we have already actually evaluated this integral, limit b approaches to infinity to the power minus p plus 1 divided by minus p plus 1, and limits are there equal to b, or it can be written as limit b approaches to infinity, and this is 1 minus p, so 1 over 1 minus p is independent of b, so we can take it out. So the limit will be applied, in fact, let's take this out and apply limit inside. So b approaches to infinity, and now by plugging in the limits, upper limit and lower limit, we have inside 1 over b minus p plus 1. In denominator, this will become p minus 1, okay? And when x is equal to 1, we have minus 1, right? So this is the result which is written here. Now since 1 minus p is greater than 0, okay, 1 minus p is greater than 0 means p minus 1 is less than 0, right? And we have already proved that if p minus 1 is less than 0, this approaches to infinity. So this approaches to infinity as p approaches to infinity, okay? So this is divergent in this interval as well, right? Therefore, the series diverges by the integral. Because this integral diverges, thus the series diverges. Now, the last case, that is when p is equal to 1. So, what happens when p is equal to 1? So, when p is equal to 1, we have the series sigma 1 over n. And we have already proved that this is the divergent series, right? And this is the divergence series we have already proved in the initial slides. So the summary of all the findings, we have convergence for p greater than 1 and divergence for every other value. Okay, next example, if we have a series 1 over sigma 1 over n square plus 1. This is not a p series, but it converges by the integral test. The function f is x is equal to 1 over x square. So first of all, we have to find the associated function, that is fx is equal to 1 over x square plus 1. What we need to check, this is positive, this is continuous, and this is decreasing. Alright, so this is positive because x square is positive for every value of x, and since x varies from 1 to infinity, so this is positive, continuous of course in this interval 1 to infinity, and decreasing as well. As x increases, this 1 over x square plus 1 decreases. So this is positive, this is continuous, this is decreasing. So we can use integral test to check the convergence. Now, in order to check the convergence, we have to evaluate the improper integral associated to this series. So integral from 1 to infinity, 1 over x square plus 1 is in fact tangent inverse of x as b approaches to infinity, or in between you can write the step limit b approaches to infinity, integral from 1 to b 1 over x square plus 1 dx. Okay, so in between you can have a step, and this is equal to limit b approaches to infinity tangent inverse x, and lower limit is 1 and upper limit is b. So by plugging in the limits, we have this result, and letting b approaches to infinity, we have tangent inverse infinity, that's pi by 2, and tangent inverse 1 is pi by 4, so we have the answer pi by 4. That is, this integral is convergent, and this means this series is convergent. Okay, this series is convergent again, and I'm telling you this again and again so that you don't forget it. It does not say that pi by 4 or any number is the sum of the series. Okay, so it does not say, so keep it in mind. This just tells us that the series is convergent. Okay, so this is not telling us the value the series converges to. Okay, Next example. Determine the convergence to divergence of the series. So again we have this series. Uh, let's try and find out the associated f, which is equal to x over ex square. And now what happens? Can we apply the test? Now n raised to 1 to infinity, so this is positive, this is decreasing as well, and this is continuous as well. So we can apply the integral test, right? So in order to apply the integral test, we have to evaluate this integral, which is associated with this function, and we can use substitution method to evaluate this integral. And by using the substitution method and evaluating, now you can I'm sure evaluate the integral, and we have this answer, that is the finite definite answer. Now since integral converges, therefore series also converges. Again, what you should keep in mind, that this is not the sum of the series, right? This just gives the information that the series is convergent. The series is not equal to, the sum is not equal to 1 over 2a. Okay, so you have to remember this fact. Next we have this series. Determine convergence to divergence of the series, and series is given by this 1 over 2 to the power natural log of n. Okay, so again we are going to associate a function fx, which is equal to 1 over 2 to the power natural log of x. Okay, now this is positive, right? This is positive when x varies from 1 to infinity. This is continuous as well, and this is decreasing function as well. As x increases, this decreases. Okay, so next step is just to evaluate this integral. Now by substitution method, we substitute that u is log x, then this implies x is equal to e to the power u, and this implies dx is equal to e u du, right? And what else is required? We have to find the limits for the new variable, and this method we learned in chapter number 5, I think last exercise 5.6. We used substitution method in order to evaluate the definite integrals, and we have to find the limits for u. Now when x is equal to 1, then u is equal to log of 1, which is equal to 0. And when x is equal to infinite, that is x which is to infinite, then log infinite is infinite. So upper limit is infinite, lower limit is 0 for the new variable. Now by substituting all the terms, we have this integral, and this is e by 2 to the power u. Okay, and you can evaluate by taking the logarithm. So you know how to evaluate this integral. You just find the antiderivative and then plug the limits, and we have we see that this integral approaches to infinity. That is, this integral is divergent. If this integral is divergent, then the associated series is divergent. Okay, so you can evaluate this integral, and you can yourself. So I should write here, do it yourself. Okay, next, error estimation. As we observed in previous slides, that this integral test does not give us the value of the sum of the series. That is, we cannot find the exact value of the series varies to n 1 to infinity, or any n. They can be some integer, any integer. This is not necessary to have one here always. So we cannot find the sum by this test. Okay, so we always have an error. As while developing the integral test, we saw that if we use the upper sum, then the actual sum of the series is greater than the area under the curve, and if we consider the lower sum, then the sum of the series is less than the area under the curve. So there is a remainder. So there is an error, there is a remainder. So how to find, or how to find the bound of the remainder, and how to estimate the error, in this section we are going to learn this. Suppose that sigma an with positive terms, so this is a must, positive term is shown to be convergent by the integral test. Okay, and we want to estimate the size of the remainder Rn, measuring the difference between the total sum S of the series and its nth partial sum Sn. So that is we wish to estimate. So Rn is defined by the exact sum of the series, total sum of the series, which is S, which is not known right now, which is S. This is just a matter of notation. So exact sum is denoted by this uppercase S minus Sn. This is the partial, nth partial sum. So exact sum is always the difference of exact sum and the nth partial sum will give us the Rn, right? So Rn is defined by this. So this is equal to an plus 1 plus an plus 2 plus an plus 3 and so on. How? Because S here is a1 plus a2 plus a3 so on plus an plus 1 and so on for infinite number of terms. This S gives us the sum of infinite number of terms, that is sum of the whole series, and Sn is the nth partial sum, that is this is equal to a1 plus a2 plus a3 an. So this is the nth partial sum. When we take the difference, that is when we have to find the S minus Sn. So what we are going to do, we are just subtracting this. Okay, so we are cancelling all these terms out, and we are left with an plus 1 plus an plus 2 and so on. So this is the remainder. So to get a lower bound for the remainder, we compare the sum of the areas of the rectangle with area under the curve y is equal to fx for x greater or equal to 1 in this way. So in this case, we see that, so an plus 1. Now in this case, rectangles are facing towards right. At n plus 1 we have this rectangle. Okay, so an plus 1 plus an plus 2, this is Rn by this definition, and this is greater than this area under the curve. This is greater or equal to area under the curve from n plus 1 to infinity. So this is one inequality, and the other inequality will be the lower sum. That is, if the rectangles are facing towards left. So in this case, we have this relation Rn is less or equal to n to infinity. So you can see in the previous slide, this it was starting from n plus 1. But in this case, when we face the rectangle towards left, we are going to start from n. So this is less or equal to n to infinity, integral from n to infinity of fx. Now, this comparison proves the following result. And this gives the bound. So this is the result we have from these two inequalities, that Rn is less or equal to n to infinity fx and greater or equal to n plus 1 to infinity fx, right? So if we add the partial sum Sn to each side of the inequalities, what we are going to have, Sn plus this Sn plus Rn, Sn plus this integral. Now Sn plus Rn is S, because Rn was defined by S minus Sn. So Sn plus Rn is S, and rest is written as it is. Okay, so we have this inequality. That is, the actual sum S lies between these two sums. So this is the bound for the remainder in the integral test. So this is how we can find the bound. This again does not give us the exact value of the sum of the series, but it gives us the upper bound and lower bound, that is S. It gives us the range where the actual sum lies. Okay, so the error can be no longer than the length of the interval containing S with endpoints given by 2. Right? So this is the bound for remainder in the integral test. Okay, let's try to find the bound with the help of examples. We can demonstrate the procedure. So estimate the sum of the series using inequality 2, and n given here is 10, that is S10. We are going to consider S10. So we have, so what we have to find? We have to find n to infinity 1 over n square x square, that is dx, and we have to find n plus 1 to infinity, right? 1 over x square dx, right? Now what is this equal to? We can see that n to infinity is equal to 1 over n. Just evaluate it and you have 1 over n. So when n is 10, this will be 1 over 10. When n is 11, n plus 1 is 11. If n is 10, then n plus 1 is 11. So when n plus 1 is 11, then its answer is, that is starting point is n, then this is 1 over n. Starting point is n plus 1, this is 1 over n plus 1, right? So as simple as this. Okay, now according to the inequality 2, we have Sn plus integral n plus 1 to infinity fx dx is less or equal to s is less or equal to n to infinity fx dx plus Sn. So this is the inequality 2. So just plug all these values into the inequality. We have n is equal to 10. So S10 plus n is 10. So 11 to infinity is 1 over 11, which is less or equal to S. And we don't know the value of S. And this less or equal to S10 plus 1 over 10. Now we have to evaluate the S10. And S10 is 1 plus 1 over 4. That is sum of 10 terms, that is we have to add first 10 terms, 1 plus 1 over 4, 1 over 9, 1 over 16 and so on up till 1 over 10 square. So this is approximately equal to, you can calculate this, is approximately equal to 1.54977. So this inequality will become 1.54977 plus 1 over 11 less or equal to s less or equal to 1.54977 plus 1 over 10. Okay, so this gives us this result. So s, this s, that is actual sum of the series s, lies between 1.64977 and 1.64068. So let's assume that this s lies in the middle midpoint of the interval. Then what is the midpoint of the interval? Just add these two and divide it by 2. So we have this result. So this is approximately the sum of this series. So the error in this approximation is less than the half of the length of the interval. So error is less than 0.005. Okay. Using the trigonometric Fourier series, we can show that this is just a remark, nothing to do with your working rule. So here is the summary of the test. What we need to do, if we have a series with positive terms and associated function is continuous, that is fx is equal to an is continuous, and decreasing function, then we have to examine the corresponding improper integral, and the series sigma an converges if this integral, improper integral, converges, where an is defined by f of n. So this is the summary. Whenever you think of applying the integral test to determine whether the series, the infinite series, is convergent, divergent, you have to follow these steps. So that's all.